Hi there, grade 10s. Today I'd like to discuss question 2 in an exam paper. This question covers the topic on waves. So the first question here, question 2.1 says, two transverse pulses, A and B, are moving towards one another in a row, as illustrated in the diagram. So pulse A has an amplitude of 3 centimeters. So the distance from the rest position to the crest of the pulse is 3 centimeters, and a pulse length of 4 centimeters. So the distance across from where the medium is disturbed to where the next point of disturbance ends is 4 centimeters. Pulse B has an amplitude of 2 centimeters. Now, it is very obvious from the diagram that pulse B, if pulse A's amplitude is taken as a positive, then pulse B has a negative amplitude of 2 centimeters. And its pulse length, the distance across, is also 4 centimeters. And it moves to the left. Question 2.11 asks for you to use a ruler and accurate measurements to illustrate the resultant disturbance in the row when the two pulses are superpositioned. So you have to use a ruler to get the accurate measurement of the pulse length as 4 centimeters across. It is also important to label what you are drawing. The resultant disturbance will have an amplitude, the vector sum of the amplitudes, vector sum of amplitude of A, which is +3, and amplitude of B, which is -2. That gives you a resultant amplitude of +1 centimeter. I see I made caused a slight problem there. So let's just fix it. So you have a positive resultant amplitude of 1 centimeter. You need to measure from the rest position up, must be exactly 1 centimeter high at the crest of the pulse. And this we usually label A plus B. So that is the disturbance that will be observed when these two pulses, B and A, are superimposed. Question 2.12 says, name the type of interference observed in the row. Now, because the resultant amplitude is smaller than any of the pulses' amplitudes, it's not 3 and it's not 2, it's smaller. It's called a destructive interference. Number 213 says, give a reason for your answer here. The resultant disturbance has a smaller amplitude than A or B. Good to go. Let's clear this. Question 2.2 also covers wave-related aspects. The diagram shows the displacement of a small boat on the surface of the water in a lake against time. The speed of the wave through the water is 9 meters per second. Here we go. This is the speed of the wave, 9 meters per second. Now, this disturbance or this wave has a distance of 3 meters from the crest of the disturbance to the trough of the disturbance. That vertical distance there is 3 meters. We have our little boat here at this point S. This point on the wavefront is 1.5 seconds away from where it started. So, first question, 2.2.1, asks us for the amplitude. Now, the amplitude is the maximum displacement of the particles of a medium from their rest position. Now, this line down the center, that represents the rest position of the medium. So from here to there would be amplitude, or from there to there would be amplitude. So my amplitude will be half of that distance that they have given on the diagram, which is 1.5 meters. Question 2.2 asks us to calculate the period of the wave. Now, there are various methods of calculating period. We all are very familiar with period is 1 over frequency. It's also an equation on the data sheet. But we tend to forget the definition of period. Period is the time taken to make a wave. So I could calculate the period by using the time that was given here and dividing it by the number of waves. That would give me the time taken to complete one wave. So here we start. One wave is completed there. 2 waves will be completed by that time, and this is half a wave. So the time here would be 1.5 divided by 2.5, which gives us an answer . Sorry for not being ready with my calculator there. 1.5 divided by 2.5 would be 0.6 seconds. So to complete this one wave will take 0.6 seconds. To reach this point takes 1.2 seconds. Right, are we good to go? Just want to clear this. define the wavelength. Define the wavelength of a wave, it says. Now, there is only one definition for this. It is the distance between two consecutive points in phase. Calculate the wavelength of the wave in number 2.2.4. Now, to calculate the wavelength, I have the period, it is 0.6 seconds, and I have the wave speed, that is 9 meters per second. I could take one of two parts. I could calculate the frequency by inverting the period. Okay, 1 over 0.6 is 1.67 if we round it off to 2 decimal places, hertz. And then use the wave equation. V equals lambda times frequency. So V is 9, lambda times frequency 1.67. So lambda is therefore the wave speed 9 divided by 1.67. Now, I've still got that answer, 1.6666666667 on my calculator. So my answer might be slightly different to the one you will get if you say 9 divided by 1.67, which is a rounded number. I'm going to times that by 9, I get an answer of 5.4 meters for wavelength. This is the one path to take. The other path to take is to combine the equation, frequency is 1 over period, and the wave equation. Let me show you how to do that. So we're going to combine these two equations. So if you replace the frequency by 1 over t, you get V equals lambda divided by period. Therefore, 9 is lambda divided by 0.6. And if you get calculate this, you get exactly the same answer. Lambda is, it will be 9 times 0.6, which is 5.4 meters. All right. 225. In which direction will the small boat be displaced when it is in the position indicated by S? So to answer this question, we need to know that a transverse wave, like this water wave, is a wave where the medium, particles in the medium will be displaced in a vertical direction. So the particles will either be moving up or be moving down. The second thing to look for is in which direction is this wave moving? Now, this wave on the diagram is moving towards the right. So this is the place where the observer will be watching what this wave is doing. So this, as this crest is moving to the right, any point on the medium here will be displaced to that position. So you can see that on the front of the wavefront, particles will be moving up. They're displaced up. After the maximum displacement, these particles that will be moving down, that's for the upward disturbance. For the downward disturbance, these particles will still be moving down. They were there, but they moved down to that position. Here, when we get to the trough here, they have stopped at their minimum or the maximum displacement. Anything from here again would be moving back to their rest position. Here, these particles have moved away from their rest position upwards. And so we can carry on. At this point here, this was the original position. This thing moved down, and it will continue moving down for a while. So the answer here is downwards. That brings us to the end of this little video clip. The next one will cover question 3.